All right, let's go ahead and get started. Drop off the test and let you go. Yeah, you got some specific examples? Okay, go for it. Yeah. Y equals 1, x equals 0. Okay, so to start, I'm not even going to ask about which method to use because I think a good thing to do right now is to do both and see what the differences are. So we know we're going to rotate around the x-axis, right? What do our curves look like? So I have x equals radical y, so that's equivalent to y equals x squared. So I have a parabola. I have y equals 1. And I have x equals 0, so that's the y-axis. So our region that we're going to make a solid out of is this one here. So I would like to find, I want to find the volume that gets made out of this solid when I revolve it around the x-axis. Do we have to use the disk method, or do we have to use the shell method? Or at this stage, are both available? Okay, so I think it's a good idea to do them both. So if I want to do the disk method or washer, really the washer is a more specific version of the disk method, but same kind of idea. If I want to set that up for the disk method or the washer method, how do I go about doing that? Find the radius. Okay. So how do I find the radius? So here's what I advise. I don't really even know what these disks look like yet. So here's the first question I'm going to ask about these disks. How are they going to be oriented? Are they going to be sitting like this, or are they going to be sitting like this? Why do you know it has to be like this? That's the key here. The fact that you're rotating around the x-axis, the only way you're going to get a disk or a washer out of the situation is if I have rectangles in here that are oriented vertically. So if I have this, and basically, no matter how many different ways we talk about integrals, they're all kind of based on the idea of a Riemann sum, which is at its heart dealing with rectangles. So if I have this rectangle, this vertical rectangle, so basically a dx rectangle, and I revolve it around the x-axis, I get a washer. I get essentially a cylinder with another cylinder removed or kind of cut out of the center of it. So I think now that we have that disk, now that we're visualizing it, now I think we have a much better chance of understanding what the radius is. First of all, does it make sense to talk about the radius as a singular thing? Do I have a disk, or do I have a solid disk with no hole in the middle, or do I have a washer? I have a washer, so I think I need to deal with not radius, but outer radius and inner radius. What is going to give me the outer radius of this solid that I'm trying to build. So another way to ask that question is further away from the axis I'm going to rotate over. In this case, got to be the higher two things. So this right here is y equals 1. So I think my outer radius is not a variable function, but simply 1, right? What is the inner radius? X squared. So we first define this as x equals radical y. But now we're saying the inner radius is x squared. Do we have to put it in terms of x, or do we have a choice? It must be in terms of x. And why is that? Why am I now stuck with doing this integral all in terms of x? Okay. It's not, it's okay. What I'm rotating around is part of the reason. But here's the thing. I could find this volume rotating around the x-axis using shells, right? So it's the fact that we're rotating around the x-axis and then I dictated disks is why we have to go with x as our variable. So, and that's something we'll talk about when we do this both ways, is that if you're rotating around an axis, like in general, you can still use disk method or shell method unless I ask you for one specifically, or one of the integrals is just not, one of the integrals is a lot simpler than the other. But in general, you have a choice. So I have my inner radius, outer radius. Can I now set up the integral? So volume is equal to what? One squared minus x squared squared. So outer radius squared minus inner radius squared dx. We need bounds, right? We know them. Should be 0 to 1, right? So this point, so this point is 0, 0. This point right here is 1, 1. So that is the integral, right? So 1 minus x to the 4th dx. I'm gonna leave it set up if that's okay. Questions on how we got there? Okay, so now I want to set this up using shells, which means I have to do some erasing because some things are going to change. Where is my... Want to do that much? Okay, I'll leave the rectangle behind. Hopefully that's okay, because it was a race into a grass solution for me. Okay, so if I want to do shells, what things change now? We need the height, right? But there's a more fundamental change we have to worry about now that we're making shells. It's going to be in terms of y this time. So now I have these horizontal rectangles, and how thick are these things? These are dy thick. So yeah, if I want to make shells, now that I rotate this rectangle around, again, the same line I was rotating over before, I'm making these thin cylindrical shells. So if I'm going to find the volume of these shells and add those all up, how do I set that up? Or what things do I need to know? I need to know the radius. And we already said it's going to be in terms of y. So radius in terms of y, height in terms of y. What is the radius going to be of these shells that I made? Should be y, right? I'm rotating around the x-axis, and what I'm looking for this time, I'm not looking at. So as y changes, see the distance, the distance of the thing I'm rotating around the axis is going to be given by y. So my radius should be that y. What about the height of these shells? How can I measure their height? Root y. Is that enough? Or 1 minus root y. So we got a couple of different conflicting votes here. So maybe let's draw, man, I'm getting really cluttered here. Let me just draw one more rectangle in here. Let me ask you this way. No matter where I draw a rectangle, how are you thinking about the height of these rectangles? Distance away from what? Distance away from root y. The distance. So I think my height is going to be something minus 0, essentially. What is the right end of this rectangle going to be given by? That's root y, right? So I think first impulse was good. So radius is y, height is root y. And I finish setting up this integral. What are the bounds? 0 to 1. Is that a coincidence, or is that always going to be the same setting it up for x and y? This is a coincidence this time. My points of intersection are 0, 0, and 1, 1. So the x bounds and the y bounds are going to be identical because my points have equal coordinates. All right, so what's the rest of this integral look like? 2 pi times the integral from 1 to 0 of y times root y dy. So y to the 3 halves dy. And I believe, at least they better, both of these integrals better give the same value. So I agree with that. Before we go on, let's make sure we did everything right. I think this one's going to come out to be x minus 1/5 x to the 5th. From 1 to 0, I believe that comes out to be 1 minus 1/5, so 4 over 5. 4 over 5 pi. What about this one? 2/5 y to the 5 halves times 2 pi. Yeah, that's also 4/5 pi, right? So yeah, unless I dictate which way, as long as the functions that are, I think we've seen examples of not remember exactly what the functions are like, but sometimes you use one method and just. Let me get a new sheet here. Where is that? No. So here's the question. I want to use the shell method, and I want to integrate on dx. That is possible, but if I'm doing both of those things, what else do I know for sure? You're rotating around, well, not necessarily the y-axis, but what? Not y equals, because y equals some value or horizontal, right? So, yes, this means, so these two things imply that we are, do y'all know this symbol here? Three dots and triangle means therefore. So if I'm using the shell method and I want to integrate with x as my variable, that means we are rotating over a vertical line, vertical axis, which hopefully that follows suit with what we just did, right? We did the shell method and we did it over a horizontal axis, which means we had to integrate on y. So said this a lot, but let's just what the axis of rotation looks like how it's oriented, horizontally or vertically. That and your choice of variables, those things together dictate this. Times being able to come up with I'll say like you can set up an integral as long as your integral is kind of structured correct. So what basically when you integrate to find a volume, the thing in here is an area, right? It's either the area of a rectangle, so that's where the 2 pi radius height comes from, or it's the area of a circle, which is where the, I'll just call it pi r squared, but really no, because it could be in and out radius. Really comes from, so let's not do a specific function, but let's say we have a region and we're going to rotate it over, we just did a vertical axis, right? Or oh, we did the x-axis. Okay, so now let's do this. Let's say it's not even the y-axis, it's going to be this, y equals 10. If I want to rotate this blob over that axis, then I can think about that in one of two ways. One of those ways is this. I make tall vertical slices like this. So if I rotate that around that axis, what am I making? That's not going to be a wash. That's going to be a thin cylindrical shell. So maybe I shouldn't draw these rectangles so thick, but if I rotate this around the axis, then yeah, basically the metaphor that the visual I kind of go to is that basically you're kind of putting the paper towels back on the roll. These shells are very, very thin, but the radius could be very large, but the actual thickness of these things is pretty small. So that's if you are doing Vertical slices, what if I do horizontal slices like this? If I rotate these around y equals 10, what's that going to look like? That's a washer because I'm taking something very long. So if I rotate it from the outer radius and then the inner radius, then unlike the thing we just made, these are not thin shells. These have, you know, a lot of area in that dimension. But where are they thin? In this height. They're terrible drawings. Hopefully they make the point that I'm trying to make them. How we do? What else? Mm-hmm. Let's at least think about this. I'm going to have an inner radius and an outer radius, right? So what can I call these things? I'll call them A and B. So these values are, actually, I don't even want to do that because this needs to be general, right? Actually, we can keep it specific here. So how would I find the inner radius of this thing? First of all, is the inner radius going to be an X value, or is it going to be like something I measure using X or something I measure using Y? How do you know it's going to be X? You're measuring the distance from something to a vertical line. That's a horizontal distance. So that's going to be something about X. So let's say this value here is X equals B. What's my radius then? My inner radius. 10 minus B is the difference between those two things. Would it make sense to say B minus 10? So I'll say this, I'll answer this in two ways. I think it does matter because you want to subtract you want your distance to be something positive, right? Negative distances don't really make sense, especially if you're trying to find a volume. If you come up with a negative volume, something went wrong. Volumes are positive quantities. So to make sure I get positive values, I want to subtract my smaller value from my larger value. What's bigger here, B or 10? 10, yeah. So I don't know what B is, but I know that's left of 10. But when you're doing the disk method, what are you going to do with your radii? So you're going to get saved by that, but let's say you're setting up shell method, you're not going to get saved there. So if this is X equals A, then what is my outer radius? 10 minus A. So that's the real difference when you are rotating around a line that is not the x-axis or the y-axis. So when you're rotating over the y-axis or the x-axis like we just did, then essentially what are you doing? You are comparing, I'm glad I wrote this down this way, you're comparing the distance of your function from 0. You're still comparing two places, so one is 0, write that down. Whereas with the one we just talked about, if we're rotating around y equals 10, you have to account for the fact that your axis, not the friendly. How are we doing? I'm talking about volume. Effective. Talk about something else for a bit. Th 3 to the n over what? 3 to the n plus 4 to the n over 7 to the n. This is a series? Okay, and I want to know what that series does. Does it converge? Does it diverge? If it does converge, do I want a sum? Do you remember what it asks? Okay. So describing the behavior of a series, I think a good place to start is let's ask about convergence. Does this thing converge? Does it diverge? How could we possibly tell? So one thing I advise if you don't have any idea, sometimes it's hard to look at these things like wholesale and get any kind of insight. So let's do this. Let's build this series out a little bit. What's the first term going to be? 1. What's the next term going to be? 25 over 49. So that's kind of a good sign, right, for convergence? Why do I say it's a good sign for convergence? I'm starting to add smaller and smaller terms, right? Ooh, let's just do one more. 27 plus 64. 64 over 243. Did we get smaller? Okay, so that's about a quarter. A little bit bigger than a quarter. So we're getting smaller, right? So maybe you believe it converges. I don't think we can say that for sure yet. Because like we have seen sequences that converge to 0, but their series don't converge at all. So here's the kind of good news about how little we've done with sequences and series so far, especially series. What kind of series do you know converge? Certain geometric series. What else? There's one we did at the very tail end of class on Wednesday. Telescoping series. That's it. That's all I'm kind of allowed to ask you about right now. So hopefully this is one of those. Is this one of those? Actually, one more thing I should bring up. We also have a thing available to us called the divergence test, right? What does the divergence test or the divergence theorem say? Go ahead. Okay, so I'm going to write this down in very short terms, but basically, yeah, there are two ways to think about this divergence test that are equivalent to each other. If the series, so if I have some sequence A sub n, if the series associated with that sequence converges, that means that the sequence itself has to converge to 0. And then what's called the contrapositive of this is also true. If this does not happen, so if A sub n, or yeah, if the sequence does not go to 0, then this doesn't happen. So the series diverges. So one thing we could check for is we could make sure that this limit goes to 0, because if it doesn't, then we really don't need to go any further. Is that a limit we can deal with, or is it still kind of tricky? By the way, is this thing right here geometric? I don't think it is, but we can treat this as series tools on it. Would we agree with this? 3 to the n plus 4 to the n over 7 to the n is equal to 3 to the n over 7 to the n plus 4 to the n over 7 to the n. Okay. Are either one of these geometric? Let's think about it. What's the first term in 3 to the n over 7 to the n? 3/7, then what? 9/49, 27 3/43. Is that what 7 cubed is? Okay. Is this geometric? Yes, it is. So this one is as well. Also, I can rewrite these as if it's 3 to the n over 7 to the n, I can just do 3 to the 7ths. I can do the division, then raise them to the n. So the thing we started with is not a geometric series, but it is the sum of 2 geometric series. So because of that, I can think about them one at a time. Do both of those geometric series converge? Yes, they do. So, and let's be very clear, why do they converge? So that is true, but that's a consequence of R is so the denominator being bigger than the numerator. That's another way. That's a consequence of the ratio being between -1 and 1. So I think based on that, we can at least say it converges, right? We're taking the sum of 2 series that converge, which means of that sum has to converge as well. Can we find the sum? Like, can we find the thing that series converges to? So if we can find the sum of both of these things, one at a time, then we can add those together. How do I find the sum of this top series, 3/7 to the n? Yeah, so what's the ratio? 3/7. What's the first term? 3/7. So 3/7 over 4/7 is 3/4. That's helpful. Do something similar with the other one. 4/7 over. So 4/7 over 3/7 equals 4/3. What is 3/4 plus 4/3? 9/12 plus 16/12. So 25/12. So I don't know if there's a way to get that sum without realizing that this can be broken down into 2 different series. So I know that if I have basically how does this fraction either I'm dividing by the numerator by the denominator and add. What else? Clean sheet. So let's think about a sequence here. Let's do a counter example first. Maybe that'll help since we just looked at an example of that converging. So let's say I have a sequence like a sub n equals 2 over n plus, or 2n plus 5n, can't speak, 2n over 5n plus 6. What does this sequence do? Does this sequence converge? Should be 2/5, right? So the sequence converges. An converges. But now I want to look at something else. What if I want to look not at the sequence, the series. So instead of just listing out all the terms and seeing what the terms go to, now I want to see what happens if I add up all these things. So let me write out what the difference is. What's the first term in this sequence going to be? 2 over 11. Then 4 over 16. 6 over 21. Okay, pattern's becoming clear now. So 8 over 26 and so on, right? So this thing, I can get as close to 0 or not 0. I can get as close to 2/5 as I want. I just have to go further and further down the list. But now what if I look at instead this 2 over 11 plus 4 over 16 plus 6 over 21 plus 8 over 26? Is that going to converge? How do I know that's not going to converge? What's good? I think I agree with you, but I want to be very clear on what you mean by the next term. Because like in the sequence, the terms get smaller as I go down, or do they not? Oh no, they don't. Never mind. So yeah, so the terms are getting bigger, right? But is there a possible way the terms could get smaller and the thing still doesn't? So basically what's going on here is let's say now instead of looking at the first few terms, let's start way down the line. What about when n is equal to 100? Then I get 200 over 506. 202 over 512. So it's getting closer and closer to 2 over 5, right? So no matter how far I go, I'm just going to stay close to 2 over 5. So what does it mean then if instead of just listing those things out, I am adding all these things up? Is this sum ever going to like converge to something? Now this goes to infinity. So all that, why did we ask that question? So basically that kind of attends to this second version, this right here. If the sequence does not go to 0, so in the case we just looked at, we had a sequence that converged to something that wasn't 0. So if it converges to something non-zero, that means the series is going to be adding non-zero things over and over and over again as n gets very big, which means your sum is going to continually change. Yeah. Yeah. Right. So I think we can say, even though we didn't look at it now, we said the series converged, right? Does that mean we can say for certain that this sequence goes to 0? It does mean that. The only way that a series can converge, if a series converges, that means in the sequence that kind of governs it has to go to 0. So we didn't actually look at the limit of that sequence, but we found the sum of the series, which means the sequence had to go to 0. So kind of we came at the divergence theorem in a lot of different directions. Any questions about any of that? Okay. What else? Go ahead. Yeah. Go ahead. And invent one. What's your favorite geometric shape? Hemisphere. totally hemispherical, right? Okay. How big is this thing? How big is the radius? 8 what? 8, cool. 8-foot radius. How full is it? Totally full? Half the way full? Half, so it's got 4 feet. The height of the water is 4 feet. Awesome. I'm gonna pump it out to a spout that's how high above the surface. What? So from the top of the pool to the top of this spout is 2 feet. Love it. Let's empty it. How? Define x. Cool. So we have a variable. What does that variable mean? Be clear, I think we have a lot of choices to make, or a lot of choices we can make. But then we have to kind of honor everything that follows that by being consistent. And I've seen a mixture of things based on conversations with you, looking at your homework and stuff. So what should we do for x? Water level? Compared to what, though? So Saul says distance from the spout. We can do that. Is that okay with everyone? So let me make a slice in here. We're going to say that x is the distance from this spout to an arbitrary slice of water. So this is x. Okay, I think that's a good. I don't think we need to verbally say what that is if we understand the diagram. Are we okay? So we know the dimensions of this tank, what its shape is, how far the water has to go. What else? How do we continue? Find the volume of that slice. Okay, I want to find the volume of that slice of water. How do I do that? Pi r squared times the height. So it sounds like you're assuming that slice of water is cylindrical. Is that fair? Okay, good. The height is going to be a dx, right? So let's catalog these things over here. Height's going to be dx. What's the radius going to be? It has to change, right? So let's think about how. We said hemisphere, which lets us make a lot of safe assumptions about things. The distance that I'm trying to draw from the center, like the center of this circle, to the edge of my slice, how far is that? Yeah, radius in all dimensions here. So that's 8 feet, right? What is this height? What's that? 8 minus x. Is it 8 minus x? I don't think it is. So if you would like to redefine x, let's think about it. Otherwise, so what would this distance be? The fact that I drew this very much not to scale is making it hard for me to see, but if I wanted to define this height in terms of x, what's the x value up here? This is x equals 0 right here, right? So I think it'd be, I don't think that helped me at all. Yeah, let's do that. I think it'd be easier to kind of. By the way, when I say you have the choice, so aggressive. All right, that's better. So now let's instead define, how do I make you go away? Okay. Now we'll say X is this distance essentially, right? X is the distance from the bottom of the pool to wherever my slice is, right? Okay, so if that's true, then let's redefine, or let's draw a new triangle here. This is still 8 feet, right? What's this vertical leg value? I think it's a lot easier to think about now. That should be 8 minus X. Okay. But I'm not really worried about the vertical, right? I'm worried about this. So how can I find, basically I'm trying to find the radius. So basically I'm looking for this thing right here, right? How do I find the radius based on things I've already developed? Are you getting all that? Okay, so say his name. All right, so r squared plus 8 minus x squared equals 8 squared, right? So I think it'd be good if we just set up the integral and walked away, seeing what's going to happen now. So 64 minus 8 minus x squared, r equals the square root of 64 minus 8 minus x squared. All right, I believe that's the radius. But no, so here's what you tried to do. Yeah, that's not true. Okay, that's my radius. And now I think I can say the volume is equal to this. Oh, you know what? I get to square the radius anyway. So volume equals pi times 64 minus 8 minus x squared times dx, right? All right, all that work was to find the volume of the water in the slice. Now that I have that volume, what can I do? I can multiply it by the density of the water, right? What is the density of water under our circumstances? 62.5 pounds per cubic foot. If it's, I don't know if it's on the test, but I'll do it. It's not, I don't care to have you memorize that. So now that I have the density and the volume, what does that allow me to do? What are the units of volume in our situation? Feet cubed. So I have feet cubed and I have some weight per unit volume. So I think multiplying those together would give me the weight, right? Or really the force. Because the force I'm trying to work against is weight. So that's the force that I want to find that'll eventually let me set up my work integral. So pi times 64 minus 8 minus x squared dx. And now do I have to multiply this thing by gravity? No. So that's something like I said, I saw a lot in the homework. Pounds are already a unit of weight, not a mass. So you don't have to account for the acceleration of gravity. Okay, so now we got the weight, the force. Now what? We need to find displacement. So let's start setting up the integral. We have a force. So pi times 64 minus 8 minus x squared dx. This is the force part of the work integral. But now I have to multiply this by the displacement, right? What's the displacement going to be? Not the bounds, but just like of my slice of water here. How far does this slice of water have to go? Well, 10 minus x, right? Because our spout is at what x value? It's 10, right? So the height of the pool is 8 feet. The spout is situated 2 feet above that. So I believe my displacement is 10 minus x. Almost done with this integral. What else has to be added to it? Our bounds. What are the bounds? 0 to what? Ooh, I heard 0 to 10, 0 to 4. Why is it 4? You told me the pool was half full by height. So I believe that integral is perfect. So bounds represent how much water you're actually pumping out in terms of water level. Force is all kind of collected, and displacement is 10 minus x. I made it disappear because the integral is not perfect. So will you allow me to squeeze in 62.5? Okay, sorry about that. Now is the integral perfect? I believe so. Yeah, good catch. Sorry about that. All right, so